But wait, there's more. The second derivative can do more than just find concavity and inflection points and all that stuff. The second derivative test, the second derivative test is actually another method that we can use to test for local extrema. So if we have a continuous second derivative on an open interval and f prime of c is equal to 0. So this part's pretty important. This only works if we have a horizontal tangent line, if our first derivative is equal to 0. If the second derivative is greater than 0, so if the second derivative is positive, then f has a local minimum at c. So let's draw this out and actually see what we can get from this. So f double prime of c is greater than 0. So what does this mean? Another way for me to say this statement right here is to say that f double prime is positive. So if my second derivative is positive, my function must be concave up. So okay, let's draw out a function which is concave up. And we started with the assumption that at our critical point, the derivative was 0. So our first derivative is equal to 0. Well, where do we have a horizontal tangent line on this graph? Well, it has to be right here at this point. And what's going on at this point right here? Yep, you bet. It is a local minimum at that point. So what we're doing is we're using the concavity of our function to determine if we have a local minimum or a local maximum. Similarly, we can look at the second case if f double prime of c is less than 0. So here, let's talk about this statement right here. If f double prime of c is less than 0, another way we can say that f double prime is negative this time. So f double prime is negative. That means my function must be concave downward. So perhaps my function looks something like this. And then, okay, again, remembering that we have a critical point whose derivative is 0, we have a horizontal tangent line. Well, where does this function have a horizontal tangent line? The only place I see is right here. And what's so special about that point? Well, it's a local maximum, and yep, you bet it, there it is, local maximum at c. If f double prime of c is equal to 0, so this is the only case we haven't talked about, if f double prime of c is equal to 0, then we need more information. This is one of the shortcomings of the second derivative test, is that it's not really going to work out for us if the second derivative is equal to 0. In that case, we would probably have to fall back to the first derivative test in order to find the local extrema in that case. So this is just another method that you can use to test and find local extrema. I don't really have a preference on which method you use unless the problem specifically states use the second derivative test or use the first derivative test. If all your problem says is find the local extrema, then I don't have a preference on whether you use the first derivative test or the second derivative test. I'll just say, you know what, just pick whichever one you think is going to be easier to use. And that may just depend on what problem we're looking at. But I want to get some practice in with the second derivative test just so that we can see it in action. We're going to use the second derivative test here to find the local extrema of a couple of different functions. First up, I've got f of x. So let's find f prime of x. So let's see, this is 3x squared minus 3x minus 36. And okay, here is my function. I want to find the local extrema, which means I need to find the critical points. So I'm going to take my derivative, 3x squared minus 3x minus 36, set it equal to 0, and solve this equation. First thing I can do, I've got a greatest common factor of 3, so x squared minus x minus, what will I have there, 12 is equal to 0. And then I will factor that quadratic. Let's see, it should be x minus 4 times x plus 3 is equal to 0, gives me x equals 4 and x equals negative 3. So these are the locations of two critical points. If we're looking for all local extrema here, in this case, I would want to think about where is my first derivative undefined here. In this case, however, we won't end up with anything, we won't end up with any extra critical points, I should say, because the first derivative is a polynomial. It exists everywhere. So our only critical points are 4 and negative 3. We don't really need to consider this case. So if I was doing the first derivative test, now would be the point in time where I'd say, okay, let's go construct our number line. Here's negative 3, here's 4. Let's plug some numbers in. But I don't want to do the first derivative test. I want to do the second derivative test. So I'm going to find the second derivative first of all, so f double prime of x. So I'm going to take the derivative of this function. So let's see, I should have 6x minus 3 and derivative of negative 36, that's 0. I'm going to take the two critical numbers that I found here, or however many critical numbers that you have, and plug those into my second derivative. And I'm interested in, do I have a positive second derivative or a negative second derivative? So let's start with 4. I want to look at f double prime of positive 4. This is 6 times 4 minus 3. So let's see, I have 24 minus 3. This is 21. In particular, this is a positive 21. So what does this mean? Be careful here. I think it's easy to kind of mix up your signs here. We have the second derivative is positive. So I always like to draw out, what does it look like? A second derivative positive. Well, if the second derivative is positive, that means that at x equals 4, we have a local minimum. Local minimum at x equals 4. So be careful with your signs. Some people, every now and then I'll even make this mistake. I'll see that positive 21 and I'll say, okay, it's a positive, it must be a maximum, but draw out your graph. Make sure that your graph, you're thinking about the second derivative being concave up. It's a very easy mistake to make. Similarly then, I'm going to take negative 3 and plug that into my second derivative. So f double prime of negative 3 is equal to 6 times negative 3 minus 3. Here I have negative 18 minus 3. This time I have a negative 21. So okay, again, sketch this out. Visualize what this looks like, negative 21. So here again we're talking about the second derivatives. The second derivative is negative. We're talking about the graph which is concave down. So at this point right here, do I have a maximum or do I have a minimum? That sure looks like a local maximum to me. So at x equals negative 3, at x equals negative 3, this is a local maximum. So at this point, that's pretty much everything I need. I can say at this point I have a local minimum, let's say at x equals 4. I have a local maximum at x equals negative 3. If we needed to go and find the y values, we would take those 2 points and plug those back into our original function f of x. So we would look at what is f of 4, what is 4 to the third power minus 3 halves times 4 squared minus 36 times 4. And I could go and find the y values if I wanted to, but at this point, I think I'm hoping we're pretty comfortable with that. We've seen a bunch of problems like this before. Really, it's this conclusion that I want to be able to draw. I think that's by far the more interesting and the newer idea here that I want to practice and get across. Let's look at one more example here. This time, this one's a little bit trickier just because it's not a polynomial. Here I have g of x is e to the x divided by x plus 1. So I'm going to start, if I want to find again extrema of the function, if I'm looking for local extrema of my function, I need to find my critical points, which means I need my first derivative. So first I need to find g prime of x. Here, let's see, this is low, it's a quotient rule, right? So low, x plus 1, d high derivative of e to the x, that's just going to be e to the x, minus high, that's e to the x, d low derivative of my denominator is just 1, all divided by x plus 1 quantity squared, square the bottom, away we go. So now we need to evaluate this and simplify it a little bit. So in my numerator, I'm going to go ahead and take this e to the x and I'll distribute that. So I have x e to the x plus e to the x. Over here, e to the x times 1, that would be minus e to the x, all over x plus 1 quantity squared. These two cancel, and I'm left with x times e to the x divided by x plus 1 quantity squared. So here is my first derivative. This is g prime of x. I need to use that to find the critical points of my function. So I'm going to, first of all, set my derivative g prime of x equal to 0. So let's see, I want to take, in this case, since it's just it's not quite a rational function, but I'm going to take the numerator of my fraction right here, set it equal to 0. So x times e to the x is equal to 0. And here I really have two factors, so I can take each factor and set it equal to 0. One is x is equal to 0. The other, e to the x, is equal to 0. If I try and solve this equation, I will end up with no solutions. If you try to take natural log of both sides, you'll find that 0 is not in the domain of natural log, which means that we have no solutions to this equation. X equals 0 is the only case. Now, the second derivative test only works for critical points where your function is where your derivative is equal to 0, where we have that horizontal tangent line. But that's not the only place that local extrema can occur. We may also want to think about, hey, where's g prime of x undefined? Where does it not exist? And in this case, I would take the denominator, x plus 1 quantity squared, set it equal to 0, gives x plus 1 equals 0, gives x equals negative 1. Well, here, this is perhaps a little bit concerning until we look at the original function. Go back and look at your original g of x, and in particular, I'm going to look at that denominator, x plus 1. If I took that denominator and set it equal to 0, I would have x equals negative 1, which means that x equals negative 1 is not in the domain of my original function g of x, which means that x equals negative 1 is not a critical point. So it may be, and I just want to emphasize this, the first derivative may change sign at negative 1. But if the function doesn't exist at negative 1, it doesn't really matter if all we're looking for is local extrema, because our function has to exist at a local extreme point. It might be a point where we change from increasing to decreasing, but if our function doesn't exist there, it's not a local extreme value. So that means that, okay, this we can ignore. We don't need to worry about that. The only critical number we are really concerned with right here is x equals 0. So I have my critical point. I want to perform the second derivative test, which means I need to find the derivative of g prime. I need to find my second derivative. I need to take the derivative of this function right here. And oh boy, this one's going to be a doozy. I have a quotient rule. Oh boy, this is a good one. This is a quotient rule. Guys, get excited. Product rule in the numerator, chain rule in the denominator. This is so exciting. Some of you might be a little bit overwhelmed saying 3 derivative rules. Please no. No thank you. I would rather not. One thing that you can do here, I often say that you don't have to factor that or FOIL that denominator out. But in cases like this, if you're like really trying to avoid having to use as many derivative rules as possible, you could FOIL that out so that you have one less derivative rule to worry about. But I think I'm up for the challenge here. I don't know about you guys. I'm feeling feisty today. So I think I'm going to try and find the derivative of this function here using all 3 of my derivative rules. All right. So g prime of x. Oops, g double prime of x. And let's make sure I've got enough room here. G double prime of x says, we'll start with the quotient rule. So low, this is x plus 1 quantity squared, d high, derivative of x times e to the x. Here is where my product rule is coming into play. So let's start with the derivative of x. Derivative of x is 1 times e to the x, plus, this time I'm going to leave x alone. This will be x times the derivative of e to the x. Well, that's just e to the x. So here is my low d high minus high. So let's see, this will be x e to the x. D low, derivative of my denominator, here is where my chain rule is occurring. So I will multiply by my power. Inside part stays the same, x plus 1 to the first power, times the derivative of the inside part. The derivative of x plus 1 would just be x, so that wasn't too bad. Square the bottom, x plus 1 quantity squared, again squared, and away we go. That, you know what? That wasn't too bad. I bet we could have added like a 4th or a 5th derivative rule if we really wanted to. For something like this, if we're using the second derivative test, I don't know that I would even bother simplifying this. Because if you think about what we want to do here, we're going to do, we could simplify this. There's a bunch of algebra that we could do here. And if we were working with the second derivative a little bit more, if we wanted to, say, find the concavity of it and determine, the inflection points and things like that, I would say, yeah, let's go ahead, let's factor it, let's simplify it. We can clean it up and make it look a little bit prettier. But if all we want to do is the second derivative test, especially because 0 is such a nice number to work with, I'm actually just going to leave it as it is here. I'm going to take g double prime of 0. This is really 0 plus 1 squared times e to the 0 plus 0 times e to the 0 minus 0 times e to the 0 times 2 times 0 plus 1 times 1 is just 1, so that part doesn't really matter all that much. 0 plus 1. If I have a squared, this is the one part I will simplify just so that it's a little bit easier. 0 plus 1 to the 4th power. And here I'm just going to encourage you to make sure you take your time here, but a lot of stuff cancels out here. So 0 plus 1, that's just going to be 1. Let's actually just figure out what's going to be 0 here, because 0 times e to the 0, that should just be 0. 0 times e to the 0, this is 0. 0 times 2 is 0. 0 times 1 is 0. So we lost that whole second half of the numerator, which is fine by me. Let's see, I will be left with 0 plus 1. This is 1 squared. E to the 0, that's just 1. Minus over on this guy right here, that's just 0. And then in my denominator, I have 0 plus 1 to the 4th. This is really 1 squared is 1 times 1 is 1 over 1 to the 4th would be 1. I end up with 1. Great, cool. Awesome, Mr. Huber. What does this mean? Well, remember we're doing the second derivative test. This is talking about g double prime right here. So what I've figured out is that at 0, my second derivative is a positive 1. Positive 1. Let's draw that out. Oops, let's do that here. Let's draw this out. If it's a positive, if my second derivative is positive, it's concave up. What's going on right there? I have a local minimum. And so I can finally conclude that I have a local minimum at x equals 0. If we wanted to find the y value, then yes, we would take that, plug it back into our original function. It actually wouldn't be all that bad. It should just be 1 over 1 or just 1. So 0, 1 if you really want to do that for yourself. But at this point, I think this video has been long enough. I think we've covered the second derivative test well enough. I'm going to go ahead and end it right there. But again, if you want the y value, remember you're looking back at your original function. You're looking at g of x, and that will tell you the y value of your function.